All right, let's dive right in. We're going to tackle a really powerful tool in maths today, the binomial expansion. And we're not just talking about the simple stuff. We're looking at expressions where that power n is, say, a negative number or even a fraction. Now, I know that might sound a bit intense, but trust me, it's a super important concept, especially when you get into things like calculus and physics, where you need to approximate tricky functions.
So let's kick things off with a question. How would you even begin to expand something like this? You've got that negative exponent, and you've got that 2 inside the bracket. It definitely looks a little tricky. But here's the deal. By the end of this explainer, you are going to have a crystal clear, repeatable method to solve this no sweat.
Okay, so here's our roadmap. First, we'll unpack the general rule and the method you need. Then, we'll jump into some practice, combining things and finding unknowns. After that, we'll tackle some more advanced problems, and then the big one, exam-style questions. And, of course, we'll finish with the key takeaways.
All right, let's get right into it. Time to build our essential toolkit for this.
Okay, so here it is, the big idea. The thing is, we can't really expand our original expression directly. It's just not in the right format. But what we can expand is something that looks like this. 1 plus u all to the power of n. We already have a formula for that. So the entire game plan, the whole trick, is to rearrange our problem by factoring out that a term. That's what gets us to a form we actually know how to handle.
And this is the process that's going to get us there every single time. It's just 4 simple steps. Step 1, factor. Step 2, identify your key parts. Step 3, expand it out. And step 4, simplify. Seriously, that's it. Factor, identify, expand, simplify. We're going to use this over and over again, so let's lock it in.
Okay, time to put our method to the test. Let's go back to that very first question we started with. Okay, let's break this down. First step, we factor. We pull that 2 out. But remember, it's inside a bracket to the power of -3, so it comes out as 2 to the power of -3. Step 2, we identify our bits and pieces. N is clearly -3, and our new u term is x over 2. Now for the expansion part. We just plug those values into the standard series formula. And the final step, simplify. That 2 to the -3 becomes 1/8, and we multiply that through. And this is super important. We have to state when this whole thing is valid. That's not just extra credit. It's a crucial part of the answer. And you can see here in this textbook example, the same logic applies even when things get a bit more complex. Here they're multiplying an expansion, but look at how it starts. It's the exact same first step. You've got to get it into that 1 plus u form. So they factor out that 4 from under the square root, and boom, you're on your way using the same method. All right, practice time. Let's dig into some textbook exercises, starting with combining expansions and finding unknowns. So question 4 is pretty cool. We expand 2 separate expressions, right? Easy enough. Then we just multiply them out. But here's the catch, the part you have to pay attention to. Look at the valid for column. You have 2 different conditions. So for the combined product to actually work, it has to work for both of the original parts. That means we have to pick the stricter, more restrictive range. In this case, that's x is less than 1/3. All right, we've gone one way from the expression to the expansion. But what if we flip it? What if you're given the answer and have to figure out what the original constants were? Let's check out question 5. So for this one, we're kind of working backwards. We start by doing the expansion, but we leave the a in there as a variable. This gives us like a template for our coefficients in terms of a. See that second column? We get 1 over a squared for the constant term. Then all we have to do is match that up with the expansion we were actually given. We see that 1 over a squared must equal 1/4, so a has to be 2. We just do that for each term to find a and b. Okay, let's ramp it up a notch. The next few problems are a bit more abstract. They're really going to test if we understand the concepts, not just how to crunch the numbers. Okay, question 6 throws a curveball. We're told that the coefficient of x squared is 3 times the coefficient of x cubed. So instead of just expanding, we have to find a. But our method doesn't change. We still follow the steps. We rewrite it, expand it out to find the coefficients for x squared and x cubed in terms of a, and then we just build an equation from the information they gave us and solve it. And once you solve that equation, you get that a is -2. It's a really clever problem because it shows that all these coefficients in the series aren't random. They're all connected by a deep mathematical pattern. Okay, this next one is a bit of a puzzle.
It's really interesting. We have a situation where a single algebraic expression can give you two expansions that look totally different from each other. So how on earth is that possible? Let's dive in.
And the answer, the whole secret, is in the validity range. It's all about that. Look at the first one. It works when the absolute value of x is greater than 2, so when x is big. The second one, it works when the absolute value of x is less than 2, when x is small. They're both correct. They're just describing the same thing in different domains. This is honestly the perfect example of why that validity range isn't just a footnote. It's a core part of the story. All right, the moment of truth. How does all of this stuff actually show up in an exam? Let's see if our method can handle some exam-style questions. So, if you look at these typical questions, you'll see the task changes a bit. Sometimes they want the first few terms. Other times, like in question 2, they just want one specific thing, like the coefficient of x cubed. But here's the thing to notice. Your approach, your fundamental method, never changes. It's always that same 4-step process: factor, identify, expand, simplify. It's your skeleton key for all of these problems.
Okay, we've covered a lot of ground. So what are the absolute key things you need to remember from all this?
It really all boils down to a few things. First, you've got to master that 4-step method. Factor, identify, expand, simplify. Just drill it until it's automatic. Second, your goal is always to rewrite the expression into that a to the n times 1 plus u to the n form. Third, and this is a big one, watch out for those negative signs and exponents when you're simplifying. It's so easy to make a small mistake there. And finally, and I can't say this enough, the range of validity is not optional. It is a critical part of your answer every single time. And that leaves us with one final pretty deep thought. This binomial series goes on forever, right? It's infinite. But for any real-world use, you can only use the first few terms as an approximation. So the big question is, when is that approximation good enough? How many terms do you need? That idea is a huge cornerstone of higher mathematics, and it's definitely something to think about as you keep going on your journey.